Here we introduce our work. We propose a new idea for semantic image synthesis. The key novelty in our work is using class-specific GANs for image synthesis. For prior work, such as SPADE, it only has a single model to generate all pixels in the result image. However, we have a separate GAN for each class, and their results are collaged together to generate the final image. There are several advantages of using class-specific models to synthesize a single image. First, we can learn dedicated weights for each class. Second, since each class is trained separately, training data can be center-aligned for each model. Third, we can use class-specific dataset to add more training data for each class. And lastly, it gives us the flexibility for object-level control, enabling more applications. Our CollageGAN consists of two types of generators. We call the first type as the base generator, which takes in entire semantic map and the instance edge map to synthesize entire image. And we call this image as the base image. Next, we have class-specific generators, which takes in mask-out target object, along with surrounding context and its corresponding semantic map. The model needs to generate a reasonable foreground based on the provided context. During inference, we first use a base model to generate the base image, and then we can recursively refine each foreground objects. Since class-specific model is trained to consider its context, thus the final image still will be harmonious. Both of our base and class-specific models share the similar encoder and decoder architecture. For example, in our base model, the encoder will process the input into a 2D spatial feature, which is then fed into the decoder. We slightly modify the StyleGAN2 architecture as our decoder. Here we show our base model comparison with the SPADE. We generate more realistic images with less artifacts compared to SPADE. Also, we generate more details, such as wrinkles in the pants. Note that this is only our base model results without being refined using class-specific models. Our base model also supports multimodal generation by sampling different Z codes. Now let's see how class-specific models can further improve image quality. The yellow inside is semantic map, and by zooming in our base image, we can see it still lacks details in certain classes, such as the chest here. We then use our class-specific models to refine classes shown in the blue inset. Now if we check the final results image, we can see more details like the straight lines and the drawers in the chest. Here is one more example, where we refine the table and the lamp. We also apply our model on human datasets. Here we see a single model is struggling on small classes or parts such as the face and shoes. But we can improve image quality using class-specific models. One more comparison between our base image and our CollageGAN, which use class-specific models. We also show the results of the cityscape dataset. Here we refine all cars. One interesting application is that we can use class-specific model to replace objects in the real image. Here we show a real image. For example, we can use a bed model to replace its original bed. Similarly to human upper clothes, note that since class-specific model considers surrounding context, thus the generated results are still consistent with its background, such as the lighting condition on the cloth. Mixed resolution is another application of our model. Here we show a 4K image, with body and background generated at a lower resolution, but face, on which we focus more, is generated in a high resolution using a face-specific model. Please refer our project page for more details.